You're listening to Masonry Principles, your guide to building better buildings, with hosts Amanda Bedian and Phil Leden.
Welcome to Masonry Principles. Today we have Jay Pease on, who's an FRP applications engineer with Owens Corning Infrastructure Solutions. But Jay works out of Ohio. The reason we have Jay on today is we're talking about the new GFRP provisions in our current edition, our 2022 TMS 402 standard. So for our listeners, GFRP is glass fiber reinforced polymer. And we'll be talking about kind of some applications, just some high level discussion about where we're going to see that being used. But we did in our 2022 standard include Appendix D, specifically on glass fiber reinforced polymer in reinforced masonry. So Jay, welcome to our show. Do you want to give our listeners a quick background introduction as far as who you are, what Owens Corning does?
Sure thing. So my name is Jay Pease. As Phil just mentioned, I am the in-house applications engineer for all of our GFRP products. These are reinforced fiberglass bars that are meant to replace conventional steel rebar. Owens Corning is a fiberglass manufacturer at our heart. Everything we make, you probably have heard of us from insulation, the pink insulation, as well as our roofing products. But we also have a division called composites. That's where we sit, making glass fiber reinforced polymer rebar. The product's been around for about 30 years. Owens Corning's been in this business for about 5, and we're really looking to grow GFRP from kind of its background. It started as a kind of a DOT solution, and now we're kind of spreading out into everything else in commercial construction, residential construction, so on and so forth. So that's kind of a little background on us and kind of what I do. I'm the engineer that solves the problems when things don't go great, or there's a question that needs answered, and I'm the guy that usually answers the question.
Awesome, thanks. So as far as the DOT, so I mean, what are some advantages that GFRP offers? I mean, why as an industry are we looking to use more GFRP compared with just traditional steel reinforcement?
So it started off in the DOTs because of corrosion. So we do not corrode. We're glass, and we're entirely made of non-metallics. So it's bars about 80% fiberglass and 20% of vinyl ester resin. Those items don't corrode. In the DOTs, I mean, if you live in my part of the world, I'm in northern Ohio, and we get a lot of snow in the winter, and what comes with that is road salts, and that's really bad on those bridges and roads, and causes corrosion, and bridges don't last as long as they're designed to. So about 30 years ago, when this kind of products first started coming online, it was predominantly to deal with that corrosion. And that's not just unique to the northern United States. In the South, if you're along the coast, in Florida or the Carolinas, you're going to have a lot of salt water. So that's really kind of where we started as a corrosion-inhibited reinforcement. Now, we've grown from there, and there's other benefits besides just corrosion. One of the biggest ones we see is the weight. We're about a quarter of the weight of steel, which works great for contractors because contractors can do more work with the same quantity of people, or transport more material with the same quantity of trucks. Things like that allow efficiencies in construction. You construct for lower cost, which everyone's always looking for ways to build things more efficiently, and it creates a better end product at the end. And finally, another benefit of us is we're non-conductive. We don't conduct any thermal or electrical currents. So what that also means is you don't get a thermal break if you put a piece of rebar through some insulation. So we have a product called Thinwall that's for precast insulated panels for concrete that, because of the nature of the material, we don't cause a thermal break. So those are just kind of some of the major benefits you see. And I guess the final one is we are more than twice the strength of steel. Your standard grade 60 steel is a 60 KSI bar. We have an ultimate tensile strength upwards of 145 KSI. So that's kind of the background of the material, what it is, why people use it. That's where we're at today.
So in terms of concrete, I know AASHTO and some of the other standards have adopted provisions for GFRP. I think ACI, don't they have a separate code 440 that specifically addresses GFRP for structural concrete? Is that right?
Yes, that's correct. So 440 ACI 440 is it's a committee within ACI. Just this past summer, about the same time TMS 402-602 2022 published, we also published ACI 440.11, which is a code, and it has now been adopted into the IBC as well. It'll be published in the 2024 IBC. And this code document 440 it's structured identically to ACI 318. So if you're familiar with concrete design using 318, 440 reads just the same way. Kind of way I like to put it is at the end of the day, we are just concrete reinforcement for 440's perspective, as well as just masonry reinforcement in TMS. The equations are a little different. The limit states are a little different. Some of the factors of safety are a little different, but the mechanics stay the same. Basic principles stay the same. So we're not really reinventing the wheel. We're more just tweaking things here and there just because of the nature of the material, but still allow your conventional design to work the same way.
Okay, well, with TMS, so in regard to masonry, we've adopted the 2022 standard, so that'll be referenced in our 2024 IVC. And so, I mean, we're a little ways off from a lot of states adopting that standard. I know in Michigan, we're still, as we record this, under our 2015 Michigan Building Code. But in the 2022 TMS 402 standard, in Appendix D, like you mentioned, Jay, I know there's a lot of equations, and what it really limits it to more than anything is non-participating elements, which I think is a good area we can spend a minute on here, kind of discussing. And so, I mean, where do you see GFRP being used in terms of masonry construction?
I mean, the immediate area I see it being used in are things like your demising walls in buildings, as well as like screen walls outside of buildings, items where you don't need to be developing large shear loads through the rebar. Something from my discussions I've had with TMS, as far as I understand it, I believe that the unreinforced masonry, if sufficient for shear loading in low seismic zones, can be used as the shear resistance and using the GFRP for out of plane force resistance. So that really does open up quite a few possibilities for applications. And that's kind of where I see this thing going from now. Another major application would be in the residential space, residential masonry walls, both above and below grade. Generally, and again, in a low seismic zone, those walls, they don't need a ton of reinforcing. And if you can use a lighter material, it's likely going to save you labor and time and transportation costs, which makes it just a lot easier at the end of the day.
So short term, I think I'm in complete alignment. I mean, I think, especially interior partitions, non-load bearing walls, those sorts of applications would be a great fit for GFRP reinforcement. And I was kind of involved in some discussions with TMS as well. And I believe you're right. If we had a shear wall or a participating wall, but it was in a low seismic zone, as long as we could use the GFRP to resist the out of plane pressures, we could design the wall as an unreinforced masonry wall as well. Have you looked at anything regarding kind of like a hybrid design where maybe you could use reinforced masonry shear walls with traditional steel reinforcement, but utilize GFRP reinforced walls elsewhere in the building?
Yeah, absolutely. That's a really key area right there. The distinguishment between the participating and non-participating walls is pretty important with this material, for now, at least within 402, 602, 2022. But oftentimes you don't need, a 150 foot long chunk of shear wall. You can deal with, a couple shear walls and then make the rest non-participating. And that's really where I can see this growing, is because the reality is that the shear walls, I mean, depending on your loading, of course, and where you are in the country and, all the caveats there, there's just a lot of masonry that you really can apply this material to in order to kind of make it more efficient from a labor and cost perspective, which is really what many contractors are kind of looking towards these days.
Sure. I mean, when we're talking about lower seismic areas, I mean, the majority of the country, I would say looking at a map is in a relatively low seismic area outside of some of our areas, near geographic faults and things like that. As far as what contractors need to know, I mean, for handling things like that, I mean, what's other than obviously it weighs a quarter of the weight of steel? I mean, is there any limitations on cutting it in the field, lap splices? I mean, what would be different if they're putting a building together with GFRP versus steel from a contractor's perspective?
Well, cutting is quite easy to do with this material. Any conventional diamond tip saw blade will go through this stuff like butter. It's pretty easy to cut. So, I mean, if you want to go buy a bunch of 20-foot sticks and you've got 10-foot tall walls, you can go cut them all in half. And I've watched guys go through a couple hundred of these things in, 20, 30 seconds. So it's pretty quick to cut. From a handling perspective, the weight is like I've mentioned before, is a big benefit. It really helps, being able to transport it, put it on a ladder rack instead of having an actual flatbed come out with all your steel, just because it's that much lighter. And finally, the workability of the material makes it a lot easier. It's more flexible than steel is, which means that you can, maneuver it easier. So that's really kind of the major benefits that you're going to see from a handling perspective. It's a lot easier to work with.
Are the resins, are they susceptible to UV damage? I mean, could it just sit on site? Yeah, I guess I don't really know all that goes into making it.
Correct. So we use a vinyl ester resin to make our bar. The resin is susceptible to long-term UV damage. So, but that's not going to really show up unless you leave it outside in the sun for a couple of years. Let's put it that way. You might see some slight discoloration in the bar. Our next generation of bars will have a UV protection lacquer that will totally eliminate it. But with what's on the market right now, there is some UV discoloration for the time being. And if in worst case, just if you're going to leave it outside for a year plus, you can just put a tarp over it, and that does the trick.
What about as far as bar sizes? Are they all still the same nominal diameters as a normal reinforcing bar? I mean, are the numbers comparable, a number 5 versus a number 5, or are they different dimensions?
All the same. We make bars number 2 to number 8 is our standard size arrangement. That's pretty standard with us. We've had historically, I mean, we try not to do it if we can avoid it. We've made larger bars, 10s, 11s, 14s, and it's all the same diameter. So a number 3 is a 3/8 inch bar. A number 4 is a 1/2 inch bar, things like that. It's all the same there. The bar might look a little different than what you're used to seeing with a conventional piece of steel rebar, but at the end of the day, we have an ASTM standard called ASTM D7957. All that means is it's just like A615 steel. There's a list of parameters the bar must meet to be qualified. All of our bars are qualified. That's the qualification that's within TMS as well. You must be an ASTM D7957 compliant material. And that goes through and that specifies your nominal bar diameters. They're the same as what you would see with steel. It specifies your strengths, your minimum strength requirements, your modulus elasticity, all the technical items, and kind of what you need in order to make sure you have a quality material. And it also means that, it's a fair playing field for all the different manufacturers of GFRP out there.
Gotcha, that makes sense. I don't want to get too in the technical weeds here, but I think the main difference, in all the literature I've reviewed is that fiberglass kind of remains in that linear elastic state, and so it has different failure mechanisms. I guess just from a high level, did you want to touch on that at all?
Yeah, and I think that kind of plays into what I was mentioning earlier with seismic. So we are a pure linear elastic material. So think of like a rubber band. You can pull on it, and pull on it, and pull on it, and eventually it just fails. So because of that, there are factors of safety within all these codes that handle this. That's a major difference. So there's no real ductility in the actual bar itself, which is definitely different than steel. It's part of what's with the limitations on the high seismic zones. You do rely heavily on ductility and high seismic. So that's a pretty major difference. The other thing you're going to see is we have a lower modulus elasticity as compared to steel, but we have much higher tensile strength. So what that works out to being is that, your pure sectional capacity of the wall might be very similar or potentially better with GFRP compared to steel. However, you might hit deformability and serviceability problems, deflections, things like that. Now, it does play pretty well with masonry in the TMS Appendix D. We do have higher wall deflection limits as compared to steel. I believe it's 0.01 for us and 0.007 for steel times height. And that's partially because we are purely linear elastic. So if we deflect, we're going to come right back to form. Our bar doesn't like deforming under load. It likes coming back to how it was.
So I guess, I mean, from an applications perspective, I mean, a lot of our states are still, like I mentioned, in Michigan, as we record today, we're still under our 2015 building code. In New York, I think you're either under 2015 or 2018. I mean, if this is in our 2022 TMS, I mean, if I'm a designer, I guess we'll start there, that wants to take advantage of GFRP, I mean, what do you see being the easiest path to use it on designs, knowing that it's not in the current building code?
So we do have an ICC ESR report. It's ESR 4593, I believe. That ESR report allows us to be used within the current iterations of the IBC, as long as we follow ACI 440. That ESR report will eventually go away as states adopt the 2024 IBC. But for the time being, that is our kind of fallback to make sure, it all works. We're all within code. The ICC, it's the International Code Council. They're the ones that oversee the International Building Code and the International Residential Code. ICC ESR is publicly available on the ICC website. And that allows you to use ACI 440, to use TMS 402, 602, 22, as long as you're within the constraints of that ICC ESR report. And the ESR report has very similar constraints that the codes do, no high seismic, things like that.
And so, I mean, let's say we're a contractor now. So we have the job that's already been designed. We want to, see if GFRP works. I mean, there'd obviously be some redesign involved, but if there was a significant enough cost differential, I mean, do you see that being a path to getting it specified on projects as well? The construction team seeing it as a value?
Yes, we do see that quite a bit. And contractors are really some of the biggest drivers for the adoption of this material. I have numerous examples of contractors that we've worked with them once, and then the next 10 projects they've got, they all want to do GFRP again. And it's purely because, anybody who's been paying attention to construction in the last while has noticed labor is a serious concern. They're saving money on labor. They're saving money on equipment. We see this in the concrete world with cages. Because we're a quarter of the weight, the cage doesn't weigh as much if you're pouring a complex seawall or something like that. So you don't need either as big of a crane or a crane at all potentially, which that's a major cost savings right there. And that's usually where we see contractors, once they switch, they just don't go back because they can update their own pricing. They're more efficient. They're getting more low bids, things like that. And that's really, really beneficial.
Amanda, I know you work a lot with contractors in the New York market. I mean, have you heard any of them talking about this?
Yeah, I haven't heard it on the radar, but it's definitely a conversation I'm going to bring up. And it kind of goes back to the services that I know Michigan thrives in with value engineering and what we're trying to touch on. And it sounds like it's something that we could look into when we're offering that service. Like, it's not just the alternative to wood to like block or brick, but have you done any projects where you've swapped out steel reinforcement for this on the value engineering side?
I have not yet, myself personally, and then I'll let Jay talk about it from his perspective. But Jay and I have worked together on kind of creating some design tools as far as how engineers could use it. And so that's definitely going to be an area of focus where I will be working with structural engineers on how to use this in current designs. And Jay, yeah, it sounds like you have been successful with that.
Yeah, I would argue that's a lot of what I do on the day to day is helping designers figure out how to use this stuff. I mean, I sit on the ACI committees that help develop this code. I'm pretty involved with TMS in the development of the Appendix D and what's going to happen going forward. TMS developed their Appendix D simultaneously to ACI developing their 440 code, which has been very beneficial and allowed us to really kind of grow things outward. And it's the value engineering aspect of it. It's reinforcing at the end of the day. We're not reinventing how you look at a wall or what you think of. I mean, your mechanics of materials are going to stay the same. And it's just a matter of figuring out how to resolve the forces. It's a rather straightforward, I believe, approach. And generally after, an hour or two of talking to an engineer, they get it and we go on from there. And the thing I always tell people is, don't go out and try and do your first GFRP project as a 3-story bearing wall structure in a medium seismic zone that also might have 140-mile-an-hour winds. That's probably not a winner. Start small, start with the simplest things, because with practice with this stuff, it comes pretty quickly. And if you've got experience doing masonry design, it's the same concepts. I mean, the way Appendix D is actually structured, I love it because it's really just a series of equations that are modifiers to Chapter 9. That's really all it is. You're going to substitute this equation in Chapter 9. That's things like lap lengths, your stress equations, how you're looking at that kind of stuff, some of your phi factors. So you're really, if you're used to doing the conventional TMS approach, all you're doing is plugging in a handful of new equations at specific points in your design methodology.
Jay, for New York, are you the national guy? Like, is there a contact for New York contractors or architects and engineers?
I'm the national guy. So
Okay.
if there are questions, send them my way. I'm more than happy to answer anything that comes up. We're growing this thing as quickly as we possibly can. And I mean, we want to learn from you guys as much as you guys can learn from us. We want to know what your best practices are. We want to know all these things because it just makes the entire ecosystem more efficient and better. I'm a lifelong learner. That's kind of how I approach everything. Is you constantly got to be learning and listening to people who may have different experiences. And I'm looking forward to that and speaking to new engineers and some problems they might have or certain issues they might have that, how do we address it and come up with the most efficient solution possible and then learn from that solution and continue to practice it going forward.
Absolutely. Thank you.
Yeah, and I think, Jay, kind of what you had talked about, where I want to push it myself, speaking for the MIM, is kind of the low-hanging fruit. Low-story commercial buildings, schools, things with a bunch of partition walls. That's where I think it would lend itself really nicely. We are doing some grout panels, looking at a few different things we want to change within the TMS for this next code cycle. And one of those things, I probably will have them grout up a panel of GFRP just to get contractor feedback. How does it work? What's different? Those sorts of things. And so that's something we'll be doing in the next probably month or two, just because some of the stuff we want to change within TMS, we want to get kind of ahead of the game on. We will have that experience. And then especially in Michigan and being very low seismic, nothing drives me crazier than the massive amounts of reinforcement we put in interior walls anyways, right? And so, if we can find a way to work on getting some of that reinforcement out of there, or using GFRP at wider spacings, I think it just makes us more economical as a system. It makes masonry easier to use. Yeah, and so those are some of the things that I'll be focusing on. Obviously, working with you and Owens Corning as well. For as old of a material as masonry is, this is nice that we're actually taking advantage of some newer technology here.
Absolutely. And I think one other thing to add about the GFRP in general is that it's a little backwards from a lot of other materials you see, whereas every time the code updates, engineers view it as getting more and more conservative, more factors of safety, things like that. With us, we started out in a really, really conservative spot. That's why we restrict seismic. It's why we have a lot of extra factors of safety. And something that's beneficial to us is, as we have now 30 years of practical background, you can go back and look through the ACI codes and see we're starting to be able to relax some of our constraints that we might have had before, because there's more and more good research coming out and showing that some of the conservatism we applied at the beginning isn't really as necessary. And that's going to be true as the codes go forward, including in seismic. Part of the reason seismic's right now not allowed isn't because it's not possible. It's just because we don't have a good way. We haven't figured out a good way to do it. And I think there's research ongoing in all of these areas. So please, we love feedback on items and areas that specifically we could look towards as we're continuing to grow the product and grow its applications into something. We want to put everybody at ease and make this as easy to use as possible and be able to fit in as many applications and let the market decide what the best solution is.
All right. Well, Jay, I really appreciate your time and being on with us today. I think, we went over a lot of the key high points. For me, the big thing is that GFRP is out there. It is permitted in masonry walls. And now we just got to figure out, where it fits, like you had said, and just let the market decide. So thanks a lot, Jay. Really appreciate you being on with us. And, for our listeners, if you have any more questions, be sure to reach out. We can definitely share Jay's contact information when this gets posted. And let's see if we can use it on some projects this year.
Thanks so much for having me on, guys. Really appreciate it.
Thank you for listening to this episode of Masonry Principles. To continue the conversation, be sure to reach out to us by visiting masonryprinciples.com.